Large language models are moving beyond single-prompt chatbots. By linking specialized models together into multi-agent systems, we can execute complex, multi-step workflows. An entity agent extracts data, a retrieval agent pulls documents, and a reasoning agent synthesizes answers. But this distributed architecture introduces a critical vulnerability. When you rely on continuous inter-agent communication, a single compromised node can broadcast malicious instructions to the rest of the network. Once malicious logic enters the communication stream, it propagates. The negative impact amplifies across the system as benign agents consume poisoned data. Modern attackers know that security filters are looking for obvious threats. To bypass them, they use semantic camouflage. The attacks are injected into inputs that mimic the exact format and linguistic style of a standard safe query. Look at this JSON array representing a prompt injection attack. The payload is buried inside the av text field. It reads as a contextually plausible sentence about sound frequencies, perfectly matching the expected data structure, yet it secretly biases the agent towards an incorrect answer. State-of-the-art defenses try to catch these threats by reading the text agents pass to each other. Because the malicious logic is completely masked by plausible language, there is a total disconnect between the safe-looking surface behavior and the corrupted reasoning happening inside the model. If the security layer only evaluates explicit textual outputs, stealthy reasoning corruption slips right past it. The current industry standard for detecting these threats relies on graph neural networks, or GNNs. Methods like G-Safeguard map out permissible communication edges between agents and monitor the network's explicit topology. These topological models are built on a very specific assumption. They require the system to operate in globally synchronized lockstep rounds, where every agent waits its turn to communicate. In practice, real-world deployments are almost entirely asynchronous. Agents operate independently, pulling from task queues and firing only when their specific dependencies are met. Without globally synchronized rounds, you get message delays and irregular execution intervals. The computation graph generated during live inference ends up looking entirely different from the graph the GNN was trained on. This temporal staleness breaks the model. When the timing doesn't match the training data, explicit topology tracking fails to identify malicious propagation. Relying on the external shape of agent communications is a dead end for modern architectures. To find the attack, we have to stop looking at the network and start looking at the antecedent internal state of the agent itself. This is where AcMAS comes in. It stands for Activation-Based Detection of Malicious Behaviors, and it shifts the security audit from the external communication topology into the internal latent space of the models. Instead of reading the text in agent outputs, AcMAS intercepts the high-dimensional hidden state vector directly from the LLM backbone. The framework targets the generation of the final token, extracting this vector from the neural network's topmost layer. By pulling from the final layer of the final token, we leverage the model's causal attention mechanism. This specific vector is forced to aggregate the entire preceding input context and all the intermediate computations. We now have a single mathematical summary of the agent's complete reasoning trajectory, captured before a character is transmitted to the rest of the network. When compromised agents process malicious logic, they exhibit highly correlated activation patterns. The math behind the deception is consistent. AcMAS collects benign execution traces, plotting normal activation vectors in a high-dimensional space to establish a safe prototype centroid. When an active agent processes a stealthy attack, its vector drifts away from this cluster. The exact cosine distance between them becomes our divergence score. If that divergence score crosses a carefully calibrated detection threshold, the system instantly flags the agent as compromised. Because this entire calculation happens locally, entirely confined within the agent-isolated vector space, we don't need any temporal alignment with the rest of the system. It works perfectly in asynchronous deployments. By measuring distributional deviation, AcMAS detects malicious intent using the geometry of the model's thoughts. The semantic camouflage on the text surface is completely bypassed. Spotting the attack is the first step, but the industry-standard mitigation is blunt isolation, removing the suspected agent from the network entirely. In a specialized multi-hop task, the workflow relies on an entity agent feeding a retrieval agent, which supplies a reasoning agent. If a traditional defense quarantines the retrieval agent, the dependency chain breaks, the reasoning agent starves, and the entire task collapses. AcMAS avoids this destruction using activation steering. Let's look back at our latent space, where an agent's vector has drifted into the malicious zone. The framework calculates a corrective vector, mathematically steering the corrupted point back toward the safe radius of the normal prototype. The strength of this correction is adaptive. Severe deviations receive maximum steering, while slight anomalies get a proportional nudge, preserving as much of the original reasoning as safely possible. This newly corrected activation is injected back into the final layer, forcing the agent to regenerate its response based on the adjusted internal state. The malicious logic is neutralized, but the agent retains enough role-specific semantics to complete its job. The multi-agent system stays online and finishes the task. When tested against graph-based baselines like BlindGuard, the data confirms the advantage of this internal approach. In asynchronous environments, topological models experience a severe performance drop. AcMAS remains synchronization robust, maintaining a 0.94 F1 score compared to the baseline's 0.38. The operational impact is just as stark. Because AcMAS steers rather than isolates, it achieves a 97% task completion rate. That near-perfect completion rate is paired with an attack success rate of just 3%. The system stops the threat without stopping the work. In production, the computational overhead is minimal. Extracting the vector and computing the distance takes up roughly 0.22% of total LLM inference time. The system provides continuous, real-time monitoring. The heavier compute cost of activation steering only engages when an anomaly is actually detected. This chart shows the detection accuracy across different LLM backbones. Whether deploying GPT-OSS, DeepSeek, Llama 3, or Qwen, AcMAS maintains over 97% accuracy, scaling consistently from 8 to 80 agents without locking you into a single architecture. And building that normal prototype for a new deployment is highly sample efficient. As this F1 curve demonstrates, performance stabilizes rapidly after observing just 20 to 50 benign execution traces. Because estimating the centroid is entirely training-free, adapting to domain shifts is computationally trivial compared to retraining a full graph neural network. As multi-agent systems handle increasingly complex tasks, trying to police the explicit text they generate is a losing battle. True security requires a geometric audit of how they think.